Hey everyone. Today we're going to look at or continue with applications, and in particular now we're going to be looking at kind of connecting something we did already, which was the graph of an exponential function, and had the form of that equation. And if you recall, the growth function was when the base of our power was greater than 1, and the graph that we got looked like that. So that was our growth function, and our decay function was when our base on our power was between 0 and 1. Sorry, messy graph. That's our decay function. And if you recall also, this y-intercept right here was the y-intercept was equal to the a value from here. Okay, let's take a look at applying that to some real-life situations. And we're going to flip to page 251 now in your workbook. Okay, page 251, we're going to look at kind of how this formula on your formula sheet, it looks like this: y equals a times b to the t over p was developed, okay? But we're going to use a specific half-life example first. Half-life is when you're dealing with radioactive substances decaying, and a half-life is really the amount of time, so an interval time h called a half-life, that it takes for half the amount of the original substance to be still radioactive. Okay, we're going to change it to fit exactly the formula on your formula sheet. So we're going to have y, you could change that in your workbook. Let y represent the amount of the radioactive substance present at time t, and let lowercase a represent the amount present initially. And for some base b, we're going to write the function as, actually we're going to write it as y equals ab to the t. Okay, so here's what we're going to do. We are going to sub in a specific situation when t is h. Okay, so we'll have y equals, sorry, let me skip the y for a minute, ab to the h. Now we're replacing time with h because only half the substance will be there. So basically our final amount will be half of what we started with. So we'll put 1/2 a when the initial amount was a and our time was h. So let me just bring that up down here so we have it to work with, more room to work with. Okay, so what we did there was we just simply replaced our final amount with 1/2 a compared to our initial amount of a, and the time taken to do that would be h, which is our half-life. And now what we want to do is solve for b, just to see if we can get the formula on our formula sheet. So first thing we would do to solve for b, which is in our power here, is to get rid of the a in front. So we're going to divide both sides by a, and now we're just down to 1/2 equals b to the h. Okay, now we're not going to log both sides because we're not trying to find h, we're trying to find the base on our power. So we are going to reciprocal exponent both sides of the equation, and that will eliminate the exponent of h on the right hand side. Okay, so now, and that was also done in a previous lesson. So now we have basically that b is equal to 1/2 to the exponent of 1 over h. And no, don't flip both of those if that's what you were thinking. Okay, and we're going to sub back into our original equation, y equals ab to the t. So again, I'm using this one that we developed in a previous lesson for the equation, the graph, just so that we can compare it to our formula sheet equation. So in for b, t still on the outside, goes 1/2 to the exponent 1 over h. Okay, now if we simplify that a little bit, we have an exponent of exponents, so we can multiply those exponents. So it's sort of like 1 over h times t over 1 is going to be t over h. Okay, so that would be basically a formula describing half-life, where h is the amount of time for half of the substance to occur. And look at our new base. It seems to be 1/2. Okay, so let's try the same scenario with doubling time. Okay, so let's say we have some sort of situation where the situation is doubling each time. So we could again develop the equation And there's not a lot of room down here, so, well, I guess we have to start it down here. A, B to the T, and we're going to let T equal, let's say P, I guess. And that's going to be our period of doubling. Oh, actually, if you want to do it like they did, we can say D. Okay, but on the formula sheet, both H and D are going to be called P, and we'll get to that. So, okay, D equals, time is D when we're doubling, and that would mean Y would now be 2 times A, so twice our original amount, okay, because we're doubling. All right, so then T becomes D. We're going to do exactly what we did before. Divide both sides by A, which means we'll have 2 equals B to the D. All right, and then we're going to do the reciprocal exponent on both sides. So 1 over D, 1 over D. Okay, and that leaves now B equals 2 to the 1 over D. Sub that back into our equation, and we would have Y equals A. In for B goes 2 to the 1 over D, and then we have T on the outside. Okay, so our equation would become 2 to the T over D. Okay, so compare it to what we did before. We had 1/2 as our base, now we have 2 as our base because we're doubling. And again, we have the period of time that it takes to do that kind of underneath our T in our formula. A is still our initial amount, Y is still our final amount. So that develops a formula. Let's take a look at the next page. Okay, and so in the workbook here, they've developed this formula. We're going to modify it a little bit to reflect the formula that's on your formula sheet that you're going to be using. So instead of basically this formula, what we're going to do is we're going to use the one from your formula sheet, which is Y equals A, B to the T over P. Okay, so if you could please change that in your workbook here, and take a look at it on your formula sheet just to confirm. Okay, our initial amount is going to be lowercase a. Okay, that's our initial amount. A, the final amount, is now Y. Okay, T is T, so that stays the same. And our base is going to be B from our equation. And our base will change depending on our question. It'll be 2 if we're doubling, 3 if we're tripling, 1/2 for half-life. Or if it's percent, it could be, for percent, you would go 1 plus 0.0 whatever the percent is. Actually, here we'll go 1 plus the interest. It's not really interest. We'll go percent over 100. Okay, and that's if it's increasing by a certain percentage. And if it's decreasing, we're going to go 1 minus whatever our percent is over 100. Okay, very similar to this first one with the plus, our compound interest formula, right? Okay, now P is still P, yay. Period of time for doubling, tripling, halving, or whatever our percent increase, decrease is growing by, the time period. Okay, so let's try this on a couple questions. We'll try example number 4 here. Patient feeling ill had a sample of bacteria taken from her throat. Oh, sounds gross. Unless you want to be a doctor, then it's kind of cool. The sample contained 387 cells. 24 hours later, the sample was recounted and found to contain 8,012 cells. Find the doubling period of the bacteria to the nearest tenth of an hour. Okay, so let's write our equation down. Y equals A, B to the T over P. Okay, so the word doubling, right away, that tells us B is equal to 2. So let's go to our equation and replace B with the 2. All right, now we're looking for the period. Okay, so because we're trying to find doubling period, the period is actually the P value. So that's what we're looking for. So both of these exponents, okay, are time units. And they have to be the same time units. So you'll notice the other time unit we were given was this, 24 hours later. So that would be our T. And then the time that that's connected to, or the amount of bacteria that's connected to, is 8,012. So that's our final amount over here, the number of bacteria. All we're missing now is our A, which is our initial amount, which our bacteria started off as 387. Okay, good. So we've got everything in our equation. Now it's just a matter of solving this exponential equation, which we learned in lesson 1 of this second chapter. So let's take a look. We have our variable in the exponent. So first thing we want to do is start peeling stuff away from the right-hand side. So we will peel away first this coefficient, 387. Kind of start from the outside when you're peeling stuff away. Okay, so now we're down to whatever this ugly number is, 8012 over 387 equals 2 to the 24 over p. Okay, now to get at that exponent, we are going to have to log both sides. So we're going to have log of 8012 over 387. Yes, you can get a number for that, but it's probably going to be one that you're going to have to round, and you don't want to round anything, because then your final answer might be off. Okay, so now we have that. Why did we do that? So that now our exponent, we can use our power rule from logarithms, so our exponent can move down front. Alright, so we now have log of that ugliness again, 8012 over 387 equals 24 over p and log times log 2. Alright, okay. Now there's the easy way and then there's the hard way to solve this. You probably want to know the easy way, right? This p is on the bottom. So what we're going to do is get it off the bottom, okay? No sense dividing by log 2 or 24 or whatever. Let's focus on p and getting p off the bottom. And how to do that, we're going to multiply both sides by p. Okay, so now we have that. Okay, now take a look at it again. Now we want to get p by itself on the left-hand side, so we're going to get rid of this log. So we are going to divide both sides by that log. Okay, and divide the right-hand side. Here we go. A lot of writing, I know. And let's just rewrite that to make it look a little prettier. So on top, we're going to have 24 log 2, because the p was gone. And then on the bottom, log of ugly number 387. Okay, there we go. Time for the calculator. We have p isolated, so off to the calculator, everyone. Okay, just a note about what you're typing into your calculator. Okay, in this function, we don't have to worry so much about putting the numerator in brackets in this case, because it will go 24 times log 2 before it does the dividing. It does things in order of bed mass from left to right, so we're okay there. If we had a 24 in front of the log on the bottom, we would want to put things in brackets on the bottom, because otherwise it would only divide by, say, that whatever number was in front here, and then it would end up multiplying by the log. Because we only have one thing on the bottom, and it's one thing because it's all inside the log, so it's just log, we don't need brackets around your denominator. Okay, so we hit enter, and we get 5 point, to the nearest tenth of an hour, 5.5. So 5.5, and how do we know that was in hours? It's because the time unit we used for t was also in hours. All right, good. Let's look at the next question. April 1986, a nuclear accident at Chernobyl contaminated the atmosphere with quantities of radioactive iodine-131. If the half-life of radioactive iodine is 8.1 days, okay, that's our p-value. Notice the time unit on it, and they mentioned half-life, so half-life means that our b value is going to be 2 in the equation. Let's just write that down. Okay. Determine the number of days. Okay, so again we're looking for a time unit. The only other one we have is t. It took for the level of radiation to reduce to 2% of the original level. Okay, well let's sub in what we know. Okay, we know b is going to be 1/2. We know we're looking for t. We have the half-life of 8.1, so we have p. And they mentioned 2% of the original level, but did they tell us our original level? No, they did not. So you could use anything. If we used the initial amount of 1, then our final amount would be 0.02. That would be the simplest for solving, but maybe the simplest for understanding would be make our, sorry, that 2 shouldn't go there, make our initial amount 100 and our final amount 2 for 2% of that. All right, we are going to finish up solving this. You could actually go ahead and solve this, and we'll look at it in the next video, part 2.